Hello again, this is Vittorio Basso again with this principle of magnetic field measurement second part. So as we've seen, we are dealing with this metrology issue related to magnetic field, and we are, let's say, in the first part we have looked at the Maxwell equations where this magnetic field is defined. Now we are analyzing an adic effect, very important for where the magnetic field appears, and this is the magnetic resonance. So magnetic resonance is a dynamic effect, so it's something related to the torque which is exerted on a magnetic moment because of the presence of a magnetic field. The equation is written in this way. So we have an important quantity which is relating the time change of the magnetization with a torque exerted, and this gamma is the gyromagnetic ratio. This is very important in physics because classical particles have a fixed gyromagnetic ratio, which is the ratio between their charge and to time their mass. But in quantum mechanics, this ratio can change. So in front of the ratio, we can have a factor which is called the Landesi factor that changes for elementary particles. So electrons, they have a G factor equal to, essentially because the magnetic moment of the electrons is due to the spin quantum number. So what is the phenomenon of magnetic resonance? If we have the magnetic moment, the magnetization, which is not aligned with the field, then we will have a torque exerted on the magnetic moment itself. Then the phenomena is called the precession. So the magnetization, the component perpendicular to the field, will rotate around the field in the positive direction if gamma is negative, or in the negative direction if gamma is positive. This is the effect. This is the purely, let's say, mechanical, reversible effect, while in reality there are, let's say, relaxation contribution that are such that the magnetization in time will try to be parallel to magnetic field, so a minimum energy situation. So the typical magnetic resonance plus relaxation will be described by equation more complicated with the Larmor with respect to Larmor precession, but essentially will be composed by one, let's say, oscillatory part and one damping part. So this is what typical magnetization in time will look like: oscillations plus decrease. The point is that this frequency, the frequency of these oscillations, is related to the magnetic field by the gyromagnetic ratio. So if we know the gyromagnetic ratio of something, for example an elementary particle, an atom, a system, or whatever, if we are able to detect the precession frequency, we have a measurement of the magnetic field. This is a method which is employed in so many instruments. What is the gyromagnetic ratio? Well, we have seen that essentially is related to the spin angular momentum, but we have very different gyromagnetic ratio if the mass of the elementary particle is different. So electrons, very small mass, they have this ratio, gyromagnetic ratio, over 2 pi, so it's a frequency over Tesla, which has this number here, written on the left, 28 gigahertz per Tesla. So if we put an electron in a field of a Tesla, we will experience a precession of its spin of 28 gigahertz. Completely different for the nucleons. If we take a proton or if we take a neutron, they have a large mass, which means smaller nuclear magnetization, smaller gyromagnetic ratio, and smaller frequency. So if we take a proton instead of an electron and we put in 1 Tesla magnetic field, we will see a frequency of 42,577 megahertz. And the other one, the minus 29, is a frequency for neutrons, much lower frequencies, so in the megahertz region. This is very interesting. And what do we know about these values? Well, they are not very well. So in the past, they have been measured with extreme care. So we know the gyromagnetic ratio for electron, for proton, for the neutron, but also for many nuclei. So here we're just the lighter ones, also for other particles like the muon and so on. Very interesting. So in principle, we have just the problem of selecting a system with electrons, with nuclei, or whatever, or atoms, and to study their magnetic resonance to build a magnetometer. Well, it would be nice if it would be like that, but it's a little bit more complicated like that, because essentially we have written an equation, a Larmor equation, where we have just put the magnetic field H. But this is not exactly correct, because the Larmor-Session equation essentially does not include only the magnetic field of Maxwell origin. So there is a problem also of definition of what is a magnetic field. So if we take Larmor-Session, we discover that what we have to put there is a sort of a effective magnetic field. So a derivative of the energy of the system with respect to its magnetization. So where's the problem? The problem is essentially that if we have a strongly interacting system, electrons very often they do feel very strong interactions. We have a contribution to this effective field, which is not only the magnetic field that we have applied, for example, with an external core. If we use solids, then we will have crystalline anisotropy giving effects. So there are a lot of side effects that change this effective field and make it large or just a small difference with the magnetic field, but there is. So where do we have the minimum, let's say, interactions? Well, essentially when we use nuclei or when we use the atomic vapors. In that case, we can use these systems as, let's say, principle for measuring the magnetic field. So nuclei are a very good source of magnetic resonance, and well, all of them are very well known. So nuclei with spin, they will have a precession in magnetic field, and metrology says it's just a very small application of this effect, because the most important effect is in analyzing chemical compounds. So here you see a list of isotopes of certain elements where these gyromagnetic ratio and magnetic moment are very well characterized. So this is a method that used essentially in chemistry to detect the quality of the chemical bonding by looking at small changes in these resonance frequencies. So these are not of them will be useful for metrology. What are the most useful too? Well, when we can define well the system essentially, and it turned out that one of the systems that can be defined quite well from the point of view of metrology are two. One is to use the proton, but not the single proton, which is not easy to realize as a system, but to use the proton of hydrogen, and especially when hydrogen is bonded in water. So liquid water at a certain temperature in a spherical sample surrounded by vacuum is a system that can be well defined, and where the measurement of the gyromagnetic ratio can be performed with very, very good reproducibility, and you find the value which is written there. Another good nuclei is the nucleus of helium-3. It's called shielded helium. Shielded means that there are all the electrons of the molecules around, essentially giving some shielding. So the shielded helium is also something that can be defined well. So if we take a spherical sample, put a low pressure of helium-3 gas. Helium-3 is quite rare, not abundant at all as helium, so it's not easy to have, surrounded by vacuum, and that's the definition of the measurements of the gyromagnetic ratio. If we consider the proton, we just have to consider that the proton itself and the proton, so-called shielded proton constant, are different. Their difference is not small, and also, let's say, we can slightly describe how this gyromagnetic ratio of the proton is measured. It requires complicated experiments. So we have to define, to isolate protons in what is called the penning trap, so an electromagnetic trap essentially, and then to perform resonance experiments, something which is and was common done, and let's say dedicated laboratory of physics and provide these very well defined values. How the gyromagnetic ratio of the shielded proton was measured? Well, essentially it was measured by a solenoid. So by producing a very uniform and calibrated field in a solenoid, by some special methods, the solenoid was devised in a way that uniformity is exceptional, 10 to the minus 8 for the region of the experiment. And then researchers, especially in many labs, many metrological labs, essentially in the 80s, have determined this value, which is now used as a sort of very well-defined value in other instruments to determine the magnetic field. Well, the use of the proton, of the gyromagnetic ratio of the precession of the proton spin is used can be used also at lower field. Then the frequencies goes down. One can really see the oscillations, and is a method that has been studied a lot also for very low fields. This is pictures and results coming from the activity in the 80s of the PTB. So by using this proton precession, essentially one can build instruments, and this is a very typical instrument, high field NMR, which is commercial, very much used. The measurement of the precession of the proton spin is made by a electronical method, which is quite complicated. So it's an amplifier based on the marginal oscillator method. It's a method, it's an instrument that it works very well for the large fields. If we take Metrolab is one of the few producers, very much with very good reputation in the world. The point is that water is not practical to use, so the producers of instrument have calibrated other materials, for example rubber, another material rich of hydrogen, but in that case the gyromagnetic ratio is slightly different. So isoprene rubber, silicone rubber, as we have said before, the bonding between atoms, hydrogen atom and something else, gives small changes in the precession frequency. These are the changes. But these are traceable, so against the water, and water is against the standard solenoid at NIS. To produce magnetic fields at such large values is not that easy with solenoids or with coils. So one very practical way is to use ferromagnets. So to use iron cores like that one, to have windings around the circuits, where we have a high permeability material, that could be iron for example, and then to concentrate the field in a gap. In this way there is a multiplication effect that can generate fields that arrive up to 2.5, 3 Tesla. So the limit is essentially the saturation of the ferromagnetic material. So in this way the fields are large, and if the electromagnet is large enough, the uniformity of the magnetic field is extremely good. And these are the common, let's say, magnetic field generation systems used in labs and also in metrology labs. Let's say, to go toward the conclusion of this second part, we look at the uncertainty in the range of the magnetic field, because we have seen we go down to the micro Tesla 10 to the minus 6. Then we have seen that with the solenoids we can arrive to a few milli Tesla 10 to the minus 3. Then with electromagnet we go up to 1 Tesla, and then we can also achieve a larger field with pulsed field coils or with superconducting solenoid and so on. So these are the methods. This is the example of what is done in the Metrology Institute of Germany, PTB. They use free precession for the low fields. They use the marginal oscillator for the larger fields. So in the end is always NMR for all fields. These are the typical instruments that are calibrated. So for the very low fields, laboratory instruments, then commercial for the large fields, and the source, field coils up to a certain level, and then electromagnets. To conclude, we just give another example on how this a calibration can be made of a coil against an NMR standard, because this is something that could be done. So one perform an NMR experiment, for example with water, with helium-3 or whatever it is, knowing the ferromagnetic constant, and then would like to calibrate another coil to use as a standard, a more practical standard to use in everyday, let's say, calibration of instruments. This is a typical budget. The gain is done with 1 millitesla range. Again, the film uniformity and the ambient field are the two crucial contributions to the uncertainty. So the better uniformity for the coil and the better let's say shielding of the ambient field is done, this gives the quality and the final uncertainty we can attribute to the coil constant. To conclude this second part, I just give some reference. So these are mainly the sources that I've used. So the book of Fausto Fiorillo, it's mainly, let's say, concentrated on magnetic material, but it contains a very nice part on measurement of the magnetic field. The Handbook of Magnetic Measurement by Tumansky is a very nice introduction, very didactical also. The book by Ripka is a collection on magnetic sensor and magnetometers. It's very much details, and the same is for the last one, which has to do mainly with the very high sensitivity magnetometers that we will see in the next part. And with this we conclude this second part, and we will do in the next the measurement methods.